Hi, this is fourth video on Ngspice. Today we are going to plot frequency response of a common source amplifier. The circuit is given here. We have one MOSFET, NMOS, and input signal which has both component DC and AC, power supply, and syntax for MOSFET is given here. That is M, it should start with letter M, and any name you want to give you can give, and drain node, gate node, source node, and bulk node. So in this diagram bulk is not explicitly shown. It means source and bulk both are shorted together. And MOSFET name, if you want to give any MOSFET name you can give here, and width and length, W width of the MOSFET and length of the MOSFET you can mention. And once we use a name for the MOSFET, we have to define it. So the syntax is dot model MOSFET name NMOS, because we are going to use here NMOS, so it should be NMOS. And for this one you have to refer a SPICE manual. So different MOS models are available. We are going to use level 1 model, where VTO means threshold voltage and Kp means it is mu and Cox, and lambda is related to the channel length modulation, and CJ, CGS0, CGDO and CGBO refers to parasitic capacitance. You can refer any SPICE manual, you will get to idea. There are many more parameters, but we are going to use only these many. And since we are going to plot frequency response, we should know how to plot dB scale. So if you want to plot output at node 2, so you can write simply like this: VDB, plot VDB of 2. So that means that is equivalent to 20 into log of voltage at 2. And if you want to plot the phase response, you can simply write plot phase V of 2. That means it will plot the phase of the voltage at this node in radians. So if you would like to have in degrees, then you have to multiply by 180 by pi into phase of this one, then you will get in the degrees. So let us see how we can plot this one. So let me open text editor. I will use Vim, and we will call this program as csamp.cir. First line is as usual comment. So Ngspice code for CS amplifier. Yes. And here we can use a single voltage source which has both components DC and AC. So, and again I have taken AC value as 1 because small signal model, while considering the small signal model, Ngspice uses linear model. So if you give AC 1, that doesn't mean you are applying a large signal. It will be considered as a small signal, because everything, the model will be the linear equivalent model of MOSFET will be used. So you can directly give AC equal to 1. But if you would like to plot transient response, then you have to apply a small signal here. Okay. So we will call V in, it is in between 1 and 0, and DC value is 1 and AC value is 1. So I am not explicitly mentioning it as a sinusoidal, because we are not performing any transient analysis. For frequency response AC analysis, we can directly give like this: DC equal to 1, AC equal to 1. Okay. Next one, MOSFET. How to define that? Syntax is given. M name I will give 1. D, the drain terminal is 2, gate terminal is 1 and source is 0. Bulk is not given, but source and bulk both are shorted together. And I will use my nMOS. My nMOS. And you have to write W and L. So use W equal to 80. You have to first design the problem and calculate these values, then you have to use. I have already done that, so I am directly going to write this. L equal to 1U. So 1 micrometer and is the length is 1 micrometer and width is 80 micrometer. Okay. So next one is the resistor. We will write RD. It is in between 3 and 2. Value is 500. Finally, power supply, that is VDD 30 and value is 3. And now we will define MOSFET, that is dot model, name of the MOSFET, that is my nMOS, and it is nothing but a nMOS device. And level 1 parameter we are using. So level 1 VTO 0.4 KP mu and Cox 200 U lambda equal to 0.01 channel length modulation CJ 2 e power minus 4. These are all belongs to this capacitor, junction capacitance or parasitic capacitance. CGSO equal to 4e minus 6. CGDO equal to 3e minus 6, and finally CGPO equal to 2e minus 7. Yes. And we will end the code. Let us save it, and in the terminal we will write Ngspice csmp.cir. CS. So it has loaded the code. You can see the first line, Ngspice code for CS amplifier. Now we can first perform a DC analysis. We can find the operating point. So for that you can use OP command. OP means operating point. And you can print all the values. Print all if you write. So you can see what is voltage at 1, voltage at 2. It is all DC values. Voltage at 3. And branch current you can see. But we are interested in plotting frequency response. For that, syntax is AC, because we are performing AC analysis, and we are considering logarithmic scale. So we will write DEC, decade scale. You can even use linear scale or octave scale. We will use decade. Usually it is plotted in the logarithmic scale. And number of points per decade. So 100 points per decade we will consider. And starting value. Let it be 10 Hertz. And final frequency, let it be 10 gigahertz. And let us plot as it has performed. Now let us plot the voltage at 2, output voltage. So plot VDB of 2, that is the syntax. Let us see that. Now you can see a typical frequency response of a common source amplifier. At low frequency also you are getting signal because we have not used any coupling capacitor. So at low frequency also you are getting gain. But at high frequency, due to junction capacitance, the gain falls. So this is a typical response of a common source amplifier. So you can again calculate 3 dB from this, and from the calculation also you can find first what is the cutoff frequency, and from the simulation you can verify it. So this is the dB scale magnitude. Now let us plot the phase. So for that syntax is plot phase of V of 2. So it will plot in radians, but we are interested in seeing the degree. So let me again plot, but I have to multiply this 180 divided by pi. It is the constant defined in Ngspice, and multiply by this. So you can see here initially 180 degree phase shift. It is a common source amplifier. Later you can see how at pole frequency it will be 90. So finally you can see phase changes from 180 to 0. Okay. So that's it. Thank you.